Welcome back to The Explainer. Today, we're going on a bit of a hidden journey, tracing an incredible path right through the very walls of the spaces we live and work in. We are going to decode the building services that literally make modern life possible. We'll start with the raw physics of invisible electrical energy, navigate our way through the strict rules of building safety, and finally arrive at the visible, beautiful result, architectural lighting. It's just a fascinating look at how engineering tames nature to light up our world. Let's get into it. So here's our roadmap for today's journey. 1. Electricity fundamentals. 2. Electrical distribution. 3. Earthing methods and safety. 4. Principles of elimination. And finally, 5. Comparing light fixtures. All right, starting us off with Section 1, Electricity Fundamentals. To really understand building services, we have to lock down two foundational concepts first. Number 1 is electric current. You can literally think of this like the actual volume of water moving through a pipe. It's the rate of flow of electric charges, and we measure this in amperes. But what actually makes that current move in the first place? Well, that's the potential difference, or what we all commonly call voltage. This is the electric pressure that's physically pushing those charges along the conductor. And without that pressure, those electrons simply are not going to flow. Now, how do these two forces interact? Enter Ohm's law. It states that voltage, the V, is equal to the current, the I, multiplied by the resistance of the conductor, which is R. It is a super simple, elegant equation, but make no mistake, it's the absolute bedrock for everything an electrical engineer does when they're designing a building's power system. Moving right along to Section 2, Electrical Distribution. You can't just run wires willy-nilly through a building. There are incredibly strict guidelines in place to prevent catastrophic overloads. For instance, did you know a single circuit shouldn't have more than 8 points on it? And the maximum power load on that one circuit shouldn't exceed 1,000 watts? To manage all this safely, miniature circuit breakers, or MCBs, are installed for every single room. They automatically interrupt the flow if a circuit overloads, which literally saves your house from a potential electrical fire. Oh, and absolutely crucial, proper earthing is required for all plug points. The actual scale of power coming in really depends on what the building is doing. We typically see two main categories here. Single-phase power is what you're going to have in most homes and small businesses. It's perfectly adequate for standard appliances and running motors up to about 5 horsepower. But if you're looking at large businesses, heavy manufacturing, or industrial setups, they require 3-phase power just to handle those massive, constant energy loads without failing. When it comes to actually wiring these buildings up, the arrangement is everything. Imagine a series circuit. Resistors are arranged in a single chain. There's only one path for the current, which means if one single thing breaks, the whole chain goes dark. No good, right? That's exactly why building distribution relies on parallel circuits. This setup provides multiple paths for the current to flow. It ensures the voltage remains exactly the same across each component, and hey, a single failed light bulb doesn't shut down your entire living room. But look, even with the best breakers and parallel setups, things go wrong. Insulation degrades over time, wires get exposed. So the really critical question becomes, where does all that excess, potentially lethal energy actually go when a system fails? Which brings us perfectly to Section 3, Earthing Methods and Safety. To handle those dangerous rogue currents, engineers use some pretty fascinating tricks, like plate earthing. Imagine a massive 60 by 60 centimeter copper plate embedded a full 3 meters underground. Notice that funnel setup at the top? That connects straight down to the plate through a pipe, which actually allows saline water to be poured in. This moisture, combined with layers of charcoal and salt surrounding the buried plate, drastically improves the Earth's conductivity so it can quickly and safely dissipate dangerous shocks. So that plate setup is one of two primary physical methods we use. The other, pipe earthing. While plate earthing uses that wide copper sheet embedded 3 meters down, pipe earthing utilizes a galvanized iron pipe, about 3 centimeters in diameter, driven 2 meters straight vertically into the ground. Both of these methods do the exact same job of connecting the building's electrical framework securely to the earth, but the choice usually just comes down to the specific soil and spatial constraints of whatever site you're building on. But honestly, whether you go with a plate or a pipe, the whole system's efficiency really hinges on the environment. Finer soil conditions, lower soil temperatures, and super importantly, greater water content all make the system work significantly better. On top of that, engineers can boost efficiency by using larger electrodes, spacing them further apart, and embedding them even deeper into the ground to ensure that when disaster strikes, the safety net works flawlessly.
All right, let's switch gears for section 4, Principles of Illumination.
Okay, so to talk about lighting without getting totally confused, we have to separate two technical terms. The first is luminous flux. This is the total raw light energy radiating out of a source every single second, and we measure it in lumens. Think of this as just the raw power of the bulb itself. Illumination, on the other hand, is the luminous flux that is actually received by a surface per unit area. We measure that in lux, and it basically tells us how much of that light is actually hitting your desk or your floor to help you see what you're doing. Just to give you a sense of scale here, check out this astonishing benchmark. 1 pure watt of electrical power translates to approximately 625 lumens of raw luminous flux. It really puts into perspective how a tiny amount of electrical pressure can yield a massive, massive amount of radiant energy. And finally, that takes us to section 5, comparing light fixtures. The lighting industry has just totally transformed over the last few decades. And honestly, it all boils down to one word: efficiency. Look at the old incandescent bulb. It only outputs a pretty dismal 8 to 18 lumens per watt. Most of its energy is literally just wasted as heat. Now compare that to a modern top-tier LED, which delivers an incredible 105 lumens per watt. This massive leap in luminous efficiency is exactly why LEDs are the absolute standard in modern building services today. But hey, before we completely throw out the old tech, we really have to appreciate the classic shapes of those old incandescent lamps: tubular, candle, flame, and globe. Even though the internal tech, a tungsten filament heating up inside an argon-filled glass envelope, is super inefficient by today's standards, those physical shapes were just so perfectly designed for ambiance and aesthetics. So much so that modern LEDs still constantly mimic these exact same profiles. And that actually leaves us with a really fascinating thought to wrap up on. We've traced this amazing journey from raw, invisible voltage all the way to a beautifully shaped, glowing bulb. But as our technology continues to push energy efficiency closer and closer to its absolute physical limits, how will the very shape and application of light continue to evolve in the spaces we build? Will we abandon the classic bulb shape entirely at some point? It's definitely something to think about the next time you flip a switch. Thanks so much for joining me on this explainer. Keep learning, and I'll catch you next time.